Controversies and early universe production.
Okay, thanks very much to the organizer for inviting me to give these lectures. So, okay, my name is Marco Gorghetto. I'm at DESY Hamburg, and my job will be to tell you about wave dark matter, which is by definition a kind of dark matter with mass smaller than around 1 eV. And the organizers divided the schools into these two sections because, as you will see, this wave dark matter will have very different properties compared to the particle dark matter you saw last week. In particular, these particles we produced non-thermally in the early universe via a mechanism that is called misalignment. And then these particles will basically this particle can be produced even if they're completely decoupled from the standard model, and in fact, in most cases, they are actually completely decoupled from the standard model. And second, these particles will be they can be detected in a way that is very different compared to normal particle dark matter, because instead of looking at the particles colliding with nuclei, we will instead look at the effect of these particles as collective field excitations that will have some effect, for instance, in terms of creating electric fields in our cavities that we can enhance recently and detect. So I will start by introducing general properties of wave dark matter. Then I will turn to, if you want, the most motivated wave dark matter particle, which is the QCD axion. So we'll just talk about the strong slip problem for a bit and motivate the QCD axion and the Alps. And then I will discuss the main mechanism with which these wave dark matter particles are produced, which is the misalignment mechanism. Basically, the fact that you can treat these particles as classical fields that are initially displaced from the minimum, and at a certain point they oscillate around the minimum of its potential, of the potential, and these oscillations basically make up the dark matter of our universe. Then I will turn to something a bit more complicated, which is the production of wave dark matter via the decay of topological effects, which are basically cosmic strings domain walls. And then at the end, if there is still time, I would like to give some general picture about the formation of structures in wave dark matter, or if you want, ultra dark matter, because you will see that these particles behave sort of differently compared to the standard cold dark matter even at cosmological scales. And these, if you want, suppress the spectrum perturbations at small scales and can leave signals. Okay, so this will be backward lectures, but sometimes I will show some movies or some plots in slides. So let's start with one. So maybe start here or nowhere. So I start here by saying that. So we know that a large part of our universe is made of dark matter, and as we heard last week from Francesco, and also we know in general, the dark matter, like the universe, at large scales, particularly cosmological scales, is homogeneous and isotropic. However, at small scales, the dark matter has inhomogeneities, and it clumps into gravitational bound objects that are basically halos. So we expect to have around, and we see that around we have dark matter halos, basically gravitational bound objects of dark matter, and these halos basically are the host of our galaxies. So what we have to reproduce in these lectures is not really the dark matter abundance, if you want, or the dark matter density inside these dark matter halos, but it's the average value of the dark matter in our universe. And this is measured via cosmological measurements, basically by Planck, and is given by omega dark matter equal to rho dark matter over rho critical. Okay, let me call it rho c. Where rho dark matter is basically the average value of the dark matter density, and it's given something around 0.5 times 10 to the minus 5 GeV. Okay, can you see? Probably no. Per cubic centimeter. Let me go bigger. Bigger, okay. So it's 0.5 10 to minus 5 GV per 0.5 10 to minus 5 GV per cubic centimeter, okay. So this density is not large, that is basically less than a proton per cubic centimeter. However, turns out that inside the matter halos and even a bit outside, the density is much larger than this. So the dark matter halos basically are bound objects where the dark matter is supposed to be virialized. And okay, and there's not really only the matter in the halos. There is structures at all scales. In particular, these halos can form clusters and okay, galaxy clusters and so on that are also bound by dark matter. And in one of these halos, the dark matter is in fact much larger than this. Let me call it the local. Is a factor 10 to the 5 larger, around time 4. So a factor 10 to the 5 larger, which is 0.4 GV per cubic centimeter. So is actually much larger. So we not have to we have to reproduce this value and not this value. And let me say that the dark matter inside these halos is in fact okay, is virialized. So in numbers, this omega dark matter, if you plug in number, is around 0.265. Okay, and this is also the order of the basically, so critical is of the order of the total energy density of the universe today. So basically, the dark matter makes up 27% of the observed energy density of the universe. So these halos are usually assumed to be virialized, and indeed there are hints from numerical simulation that indeed these things are virialized. So since many times they are virialized, we can in fact use the virial theorem to understand what is the velocity of the dark matter, just an order of magnitude estimate, what is the velocity of the dark matter inside these halos. And so virial theorem, assuming that these halos are stable, gravitationally bound, and in equilibrium, virial theorem will tell me that twice the kinetic energy of the dark matter in these objects is around is equal to minus the potential energy. So kinetic energy, I can write it as something like a half mv squared. So here I'm very rough. So m would be the mass of the total dark matter inside my halo, and the potential I can write it roughly as g m okay, twice the mass squared over the radius. No. Okay, and from this now, if you use equality, I get very roughly that the mass, the velocity I expect is over the, okay, then there's a 2 here, is over the gm over r. No, and if I plug in numbers for instance for the Milky Way, for instance m 10 to the 12 or 11 solar masses and r over the 10 to 100 kiloparsec, so this is something like 10 to 11, 10 to 12 solar masses, m sun. And here is 10 to maybe 100 kilo, okay, it depends on the galaxy. So this number is around 10 to the minus 3. So we learned that around us, the dark matter is has an energy density larger than the average one. Plus, it is very non-relativistic, has a velocity of order 10 to the minus 3. Okay, so this is just the general picture of what we need to know if we want to detect these particles in a detector. And so, as a second thing that I want to do before discussing motivations for these particles is to try to classify the dark matter particles in terms of their mass. And we'll see we'll see for what or properties of the dark matter will occur for the if the mass is too small. So and okay, and I will use these properties, in particular the dark matter density and the velocity. So now I'll draw, yeah, bigger, yeah. Yeah, C is 1. Okay, sorry, maybe I didn't. So I'm using natural units, where C is 1. Okay, maybe I didn't ask the important questions. How many of you are theorists? Okay, theorists usually use C equal to 1. Experimentalists, how many? Experimentalists? Okay. So C is 1, H bar equal to 1. G, Newton constant is not 1. So this thing is not 1. But okay, some people actually use it 1. So I will write it bigger. Sorry for my. So let me now assume that whatever this stuff is a particle, is a fundamental particle, in fact, with mass m. So I have a fundamental particle with mass m. So this kind of fluid is made of this fundamental particle of mass m, and I want to classify, oops, the possible value of the masses of this particle, just via consideration, just based on these considerations, very basic considerations on the dark matter density and velocity. So there is a lower bound that we'll discuss soon, that is around 10 to minus 22 eV. And then, okay, it's possible there's an upper bound at around m Planck, which is twice 10 to the 18 GV. Okay, this basically comes from theory, but of course you can have even the matter with larger masses as long as they're not fundamental, like you can have composite particles. And in between there is an interesting point, which is around 1 eV, that I will discuss now. In fact, is around 30 eV, where the dark matter will behave differently in one side and the other, because of the large occupation numbers. Okay, before going there, I would like to, okay, maybe Francesco already did it last week, but I would like to discuss a bound on the dark matter mass, assuming that this has been produced thermally, because it might be that dark matter can be produced thermally in all this range. So I don't even have to think about non-thermal production, but in fact there is a bound, maybe at around 1 kV. Okay, let me write it here, 1 kV. Where below which the dark matter cannot actually be produced thermally, and as a result, the dark matter we will discuss in this lecture below this cannot actually be produced thermally. And the argument goes as follows. So it's called thermal dark matter bound. Okay, thermal dark matter bound. Or if you want worm, okay, worm. So the idea is that if particles are produced thermally, as you learned last week, means that they were basically in thermal equilibrium with the standard model, and the abundance is set by the decoupling from a standard model. And the idea is that coupling cannot happen too late. Otherwise, the particles that produce, like the particles that produce from this decoupling, will free stream over cosmological distances, and this is without because they would destroy the initial dark matter perturbations we need to explain the structures of our universe. So turns out that initially there were some dark matter perturbations, maybe seeded by inflation. Here there's supposed to be dark matter perturbations. And it turns out that if indeed these particles are produced thermally with too small mass, then they would free stream over a distance which is sort of large, and therefore they would reduce basically deplete the over density and making them basically flat over large distances. And the argument goes as follows. So, and I want to compute very briefly what is the typical distance where this happens, no, as a function of the of the of the dark matter mass. So this distance is called the free streaming distance, lambda free streaming, no. So just to say, this can be obtained in the following way. So these particles will be produced thermally at a temperature which is more or less okay with a momentum which is more or less equal to the temperature when they're produced. There's a factor, in fact, okay, over the 20th or 30th, and at that point the particles will be sort of relativistic, or maybe a bit non-relativistic, but they still have large momentum. And the idea is that this lambda free streaming is basically the path that the particles have been have done, the distant particles have done at but at a time when they become non-relativistic. So will be a time when they become non-relativistic, and very roughly, this distance is of the order of the Hubble parameter of the Hubble radius at the time when they become non-relativistic. Okay, because imagine these things are produced thermally. They have a large momentum. The typical distance, the maximum distance that they can travel is more or less the time of the Hubble radius at the time when they become non-relativistic. After that point, they go very, very slowly, so they don't travel anymore. Okay, then you have to trust me because, okay, but in principle, Francesco already told you last week that in the radiation illumination, this Hubble parameter can be related to the temperature of the universe. So first of all, this decoupling needs to occur during the radiation illumination. Okay, it can occur also before, but at least in radiation illumination, cannot occur in matter illumination. Otherwise, we are very ruled out. And the parameter, you know, that is the temperature. Okay, very roughly the temperature at the time when it becomes a non-relativistic square over m Planck. No. Okay, and this temperature is more or less okay. This temperature is over the order of the mass, more or less, except for a factor of 120 or 130. What's that? Thank you. So now this will be the distance that they traveled, let's say, at this time. It's this time relativistic. Then this distances stretch because universe is expanding. The stretch, so the lambda, this free streaming distance today will be given by the one at this time, so this stuff here, multiplied by the ratio scale factors. And the ratio scale factors, okay, the scale factor, let me call it A, let's say today, which is 1, divided by A at this T non-relativistic. This ratio, okay, so the distance is increased proportion to the scale factor. This ratio can be obtained as the ratio of basically the entropy densities, because the entropy density is conserved, as you probably saw last week. But I will review this in maybe tomorrow. And the entropy densities can be related to the ratio of temperatures modulo the variation of number of degrees of freedom. So this can be written like the temperature, let's say.
Sorry, what is that? Because A0 over what?
Sorry, my handwriting very bad. So the time when these particles become non-relativistic, this T and R. So particles become relativistic, okay, which is basically when the temperature of the universe is T and R. Okay, and this ratio would be T and R divided T0, where T0 would be the temperature of the CMB photons today. Okay, so which is around 10 to the minus 4 eV. Okay, if I plug this in, I obtain something like Okay, it turns out that stuff cancels, and in the end you get M Planck from here, and then you have small m, and okay, sorry, you have T relativistic, and then you have T0. And this, okay, this is just plugging in the numbers. Okay, and then plug the actual numerical values. This is over the 0.1 megaparsec for 1 kV over m. Okay, so we learned that this okay, so in these steps, this step I actually substituted with relativistic with m, just because these things the two are related by except for this factor of 120 or 130. But of course, I'm not going to take that into account because this calculation is very rough. But the idea is that okay, this is a macroscopic distance. This is a distance of order 0.1 megaparsec for m over the 1 kV. This means that if these particles are very light, below 1 kV, then they would erase the perturbations over these super cosmological distances, and this is excluded. So what people, okay, the argument goes that you have to impose that this is smaller, let's say, than the size of a typical galaxy. For instance, this one, ours. Okay, but this argument is very rough. Then to do it more precisely, you have to do calculation properly, which is 0.1 megaparsec. Okay, let's say, and therefore this implies that m, the thermal dark matter bound, should be larger than about 1 kV. So, long story short, in order to not raise fluctuations, to basically support structure formation, the thermal dark matter should be larger than 1 kV. Of course, this is a very rough argument, then people do it properly, like they consider the full dark matter space distribution of dark matter produced thermally, and they actually do proper numerical simulations of structure formation. No, they include this warm thermal dark matter, and they run m-value simulations to see the formation of structures, and they compare the power spectrum. But this is a very rough argument that tells you that in the regime that we will be interested in, the dark matter cannot be produced thermally. And the rough reasoning is that dark matter cannot be produced thermally because for smaller masses, because very small mass corresponds to very late decoupling, because it means that very late decoupling from thermal bath. And if particles are decoupled very late, they don't have time to redshift enough to become basically non-relativistic by the time of maturation equality. And as a result, no, they have to be heavy to have decoupled early enough. Okay, so good. This one is next slide. So this one, I'm going to talk about these two. We're going to talk about now. This one I'm going to talk about now. So this just to tell you that indeed we don't expect that for the masses that we'll talk about now, the dark matter is produced thermally, and so we will need the other production mechanisms that are the so-called mesoline. Of course, there will be can be other production mechanisms compared to what I'm going to talk about. So the other two limits are obtained as follows. So what I'm going to do now is ask a very simple question: is what is the occupation number of the states, the quantum states of my dark matter particles, of the my dark matter inside the dark matter halos? So the occupation number is defined, so any occupation is defined to be basically the number of particles in some volume, okay, in physical space and space divided by the volume itself, okay, in physical space, in phase space. What does it mean? It means that I take a volume in space, delta x cube, and then I take a volume in phase space. Okay, it will be in momentum space, and okay, and then I count the number of particles inside that volume with that spread in momentum. No, so I have a momentum. Okay, okay, let's say, okay, here I have that delta x cube. Okay, some delta x, and then I have the same in the same momentum space, and I count the number of particles. So this number is in fact the number of particles per W volume. So the idea is the following. So instead of, so I am smart, and I'm actually taking as delta x and delta p. So I'm taking delta x, for example, this volume here, and delta p I'm taking the volume, the momentum spread of the or that matter that is of the momentum, the momenta that are usually occupied. Momenta that are usually occupied of that kind. So delta p is usually occupied is of the order of m delta v. Okay, let me write it bigger, m delta v. Where delta v is of order v. So let me tell you one thing. So there we actually computed the very estimate computation of the typical velocity. In fact, the dark matter have not only a certain velocity, but they have also velocity dispersion. No, so in this delta v corresponds to the velocity dispersion. So what people usually do, and this is basically we know from this mostly from numerical simulations of the dark matter halos that okay, the dark matter has some velocity dispersion f of v, okay, respect to v. Velocity dispersion is maybe peaked at around this 10 to the minus 3. No, so this 10 to the minus 3 is basically obtained by that argument, but okay, not only you have this average value, but you also have some dispersion delta v that is over the peak itself. No, so dispersion means that the particles, it's not like everybody has the same velocity. It's not like, but they are moving in different directions, but they have this with some dispersion. And this is basically obtained, okay, from this visualization argument or by numerical simulations and by simulations of the dark matter. Anyway, just to say that this delta v is supposed to be over the v. So what I'm doing now, I am taking as delta p the typical momenta that are occupied. No, so I'm taking delta p, this stuff here, 10 to the minus 3. Okay, it's around 10 to the minus 3. So if I do that, then this this becomes basically the number of particles per W volume. So follow me on this one. So this stuff here is the energy density of the dark matter, the local one, divided by the mass, because this will be the number density of particles. This is the number density, so it's the energy density divided by the mass. And that is one of the delta p cube is basically the W volume, where I define the W wavelength as okay, maybe 2 pi over mv. No, so this would be the W, more or less the W volume cube, the wavelength cube. Okay, because just take delta p or take the E. Okay. So this means that this occupation number that counts the number of particles basically in the same quantum state. If I take this delta p to be the typical momentum that are occupied, is the number of particles per W volume. So I take a W volume and just count the number of particles there. And now I actually plug in numbers. So rho local was that number there. And m is m, and lambda w is that value here and there. And if you plug numbers in, you get something of order 1, no? And then I have 10 to minus 3 over v. And then I have 1 ev, so 30 v, sorry, 30 v divided by m. to the fourth. So this just plugging in numbers. So this other one factor, in fact, depends on where you take the density, because okay, so, around us, like 8 kilopascal from the galactic center, let's say, is some number, but a bit on the center is larger. So this number is really just other one factor. So we learn the following thing, that the nanoparticle in the same quantum state depends very much on the mass. In particular, if the mass is larger than 30 V, so there's the reason why I put 30 V there, this occupation number is much smaller than 1. It goes very rapidly, much smaller than 1. So inside the 1 W volume, there's not even one particle. So I have my W volume, and sometimes there's a particle, sometimes there's no particle. If M. Sorry, of course. So if the mass is much larger than 30 V, there's basically no particle inside the volume. So there's nothing. And this is the case of WIMPs. So in terms of WIMPs, this particle are very separated. So basically, this will be supposed to be a wave somewhere, but then there's nothing like anywhere. These particles are very localized in space. And so the first implication is that in this case, the particle, the particle can if the mass is smaller than 30 V, the particle cannot be a fermion. So let's say if mass is much smaller than 30 V, the opposite happens. No, all the particles have overlapping with each other with the W wavelength that is overlapping with each other. So this is the case, for example, of WIMPs, or like massive particles, and this is the case of our wave dark matter. Okay, just a few comments. So the dependence of this m to the fourth comes from the fact that so the fourth power comes, so first of all, from three powers come from the W wavelength. So if I decrease the mass, I increase the W wavelength, so the W volume, and this gives me 3 powers of the mass. And the other power comes from the fact that if I decrease the mass, I need to put more particle to obtain the same dark matter density. So this very general, very obvious why you have this dependence of 4 power. And let me also say that this number becomes macroscopic. We simply have to go in that it's 4 power. The number becomes macroscopic very fast. Becomes macroscopic when the mass is much smaller. This number becomes maybe even 10 to the 20, 10 to the 30, and so on, even 10 to the 40. Okay, becomes very large. So the first implication is that in this case, below this mass, the particle cannot be a fermion, because fermions they obey the Pauli exclusion principle, where basically you cannot have more than one fermion with the same internal quantum numbers and species inside the same quantum state, because since it obeys the Pauli exclusion principle, if you have 2 fermions of the kind, the wave function, quantum mechanical wave function, would be 0. So very roughly, here you have a fermion, can be a fermion plus boson, boson. Below here, it can only be a boson. This is known as Gantt-Tremaine bound, which is in fact much more precise than this. People have done more proper analysis with considering dwarf galaxies with larger densities. This bound maybe is a factor of 10 to the 10 larger than this. Okay, maybe 100 eV or more. But okay, but the idea is that you cannot really have fermions because they will be in the same quantum states if they were below 30 V, and so the wave function will be 0. So we learn another thing, therefore, that we have to consider bosons and no fermions. Of course, you can play with internal quantum numbers. Now you can have fermions with different forms of spins, like electrons in the orbital. So you can have maybe two fermions in the same, or maybe you can start increasing the number of species. Like you can have like a lot of species so that they can stay in the same quantum number. But this goes like to the fourth. So you have to increase sort of power like the number of fermions to be below this 30 eV. You have to increase a lot. So for instance, if you have to have very light mass, then you have to have like 10 to the 30 or 10 to the 30 different species of fermions to have the dark matter. Anyway, it's just a comment. So and the last thing, of course, is the fact that below 30 eV you have to be a boson. So bosons are basically scalars or vector bosons, can be also digravitons. But let me explain why I put the 10 to minus 22 there. I put the 10 to minus 22 because it's not that you can increase the W wavelength as much as you wish, because intuitively the W wavelength cannot be larger than the galactic halo itself. So in principle, the material is made of a bunch of particles. These particles will have some W wavelength, which okay, just it's like this, no? But you can't really have this W wavelength very large, because if it were so large, then it would be even larger than the galactic halo itself, no? And if it's larger than the galactic halo itself, intuitively you can't really have a bound clamp, just because the particles will just be larger than the clamp itself. So these are intuitive arguments where we will make more precise at the end of the lectures of why the W wavelength cannot be larger than the galactic halo. So the W wavelength, if you do the calculation as a function of the mass, okay, already written here, this is around, I think something like 1 kilometer for 10 to the minus 6 eV. 6. 10 to the minus 6 is important for the QCD, for the QCD axion over m. Okay, then I took V10 to the minus 3. So, and if you plug numbers in, this is also over the parsec, let's say maybe, 3 kiloparsec, let's say, for the mass 10 to the minus 22 over m. Okay, maybe this number is a bit off. So the idea is that if even larger than 10 to the minus 22, then the W wavelength will be larger than the galactic halo itself, and this cannot be. And this is the reason why there's this bound here. Okay, this is more or less all what I wanted to say about the dark matter particle mass. So in the end, all the discussion tells me that if I want to look for the dark matter with mass more than 1 eV, it must be produced non-thermally, it must be a boson. Okay, and in fact, God came to our help, and it's automatic. Like if you have a particle in your Lagrangian with these properties, mass below 1 eV, even without the interaction with the standard model, is actually produced automatically. And this maybe in the interesting part of the discussion. Okay. Questions? This one? Well, the fact that it's just basically the auxiliary principle. No, the particle will have a larger W wavelength, so it's not localized in a fixed volume. It will be localized in a volume of this order. Suppose that the mass is 10 to the minus 28 eV, then the particle will have a W wavelength which is let's say a factor of 10 to the 6 larger than our galaxy. But this cannot be, no? It will be like this. This cannot be because in principle you wouldn't form a bound object of those particles. These are a rough argument. In practice, this means that These objects are not formed because of something called quantum pressure of the bosons that we'll see maybe last week, last lecture if we have time. Quantum pressure prevents the formation of those objects and also even larger structures, basically, and even large-scale structures, and that's actually where the most rebound bounds on this particle come from. So no, so in this regime, the dark matter is light, and the accretion number is macroscopic. And so the story goes that in this regime, in fact, the evolution of dark matter is very well approximated via the classical equations of motion, because quantum fluctuations around the classical equation, the classical solution will be small, but it will be suppressed by the occupation number of particles. So it's a very good approximation to consider the multi-particle state, the multi-particle wave function that describes the dark matter particles, and evolve this multi-particle wave function, if you want, classically, because basically quantum fluctuations around it will be suppressed by the occupation number. And so long story short, this particle satisfy the classical equation of motion, very classical. But you know what are the classical equation of motion for a scalar field, free scalar field? These are the Klein-Gordon equations in the relativistic limit. So these are the Klein-Gordon equation, Klein-Gordon. Okay, which in the non-relativistic limit become the Schrödinger equation. And you know also what are the solutions to this equation. These are waves, and this is basically the reason why this is called wave dark matter, because the classical equation of motion are Klein-Gordon equation, the free solutions are waves, and therefore this is wave dark matter. Okay, last thing, given that these particles are very overlapping with each other, this means that also the self-interactions should be very, very small. So you shouldn't expect big self-interactions. Because if it were large, given that they're all overlapping, they would be super ruled out, especially at large scales. So now what we do is we solve these equations of motion in our galactic halo, and we see the properties, the properties of the dark matter that we expect. So, and I consider a scalar boson, not a vector boson, although in this regime the vector boson is more or less similar. So how many of you know what are the Klein-Gordon equations? Who doesn't know? Okay. So I consider now a scalar field phi. Okay, let me say that in principle you can do this stuff also for a vector boson, and even the graviton. In this regime. However, it turns out that the scalar is the most robust, in the sense that the scalar turns out to be automatically produced in the universe, as opposed to the vector boson for which you actually need to do some exercise, some work to make it produce as dark matter. The scalar seems to be very robust and almost automatically produced. I will not talk about, in fact, a vector boson dark matter because I don't have time, but you can ask me, or you can ask Sujit, who has a paper on that. So scalar field will have Lagrangian of the kind a half d phi square minus a half m square phi square. Okay. Equation of motion are box d mu plus m square phi equal to 0. So this d mu means basically dt square minus dx square. Okay. So what are the solutions of this? Okay, as you see, I'm considering just a free scalar without self-interactions. First of all, without interaction, also without gravitational interaction. So in principle, this should be a covariant derivative where you have the metric, so you have some gravitational potential. Then in principle, these particles also interact with themselves. Gravitational interact with themselves, so that to form halos. But at least locally in our halos one we're here, for a small period of time, I can approximate the evolution with these equations. Solutions are waves. So one solution, like I can write phi1 of x equal to, okay, so solution given phi 0 times the cosine of omega kt minus k vector dot x plus some phase, completely undetermined phase. So this is a solution, clearly, where if omega k is equal to square root of m squared plus k squared, this comes from the equations of motion. This constraint comes from the equation of motion. And okay, and we say in this regime, if you are sort of in the peak of the distribution, not of course in the tail, this is of order m 1 plus v squared over 2. Okay, because k is okay, k is mv. Okay. So what does this mean? Well, this means that this field looks like indeed a scalar wave. Okay, and second, at a certain point x, this field oscillates coherently. So if I take a point, let's say here x equal to 0, so evaluate phi x equal to 0. What I get is a phi of t. No, really looks like a cosine of t. No, so is a perfect cosine with typical frequency. Okay, given by 2 pi over m. In principle, m 1 plus c with the small collection. This collection is of order 10 to the minus 6 because it's v squared if you take in the bike. Okay, and this basically is also known as a Compton wave. It is a Compton wavelength of a field, and okay, it's a factor, if you want, 10 to the 3 smaller than the WG, and it's 1 meter. Let's say 1 meter. Okay, in terms of in terms of time, okay, in terms of space is 1 meter for 10 to the minus 6 over m. Okay, so okay, this means that the field oscillates. The field, in fact, in a certain point, it looks really a cosine. In fact, this is wrong because we don't really have only one wave. We have a lot of them. So this is only one solution. The most general one is a superposition of these. So the generic one, x. Okay, here there's x and t, of course. X and t is in fact given by a superposition of these. Superposition looks like integral in d3k over 2 pi cube, and then I have 1 over 2 omega k, whatever, square root. And then I have a of k, some coefficient a of k, e to the minus I, e to the plus I omega kt minus kx. Okay. The phase I have take this phase is inside A plus the convex conjugate. So this will be my most general solution. Where this a of k now not only one, there's a number of them. A basically are the square root of this f. A this follow this Dirkmaner distribution. In particular, more precisely, A star, if you want, the expectation value over the statistical average is proportional to this f of v, which is okay, f of k, let's say, this f. So let me call it f of k v. okay, then it will be a delta 3, okay, minus k prime. Okay, just to say that these A are distributed in this way. So there's a supervision of them. So the situation is not that simple. No, there are waves going on, and at a certain position x, however, at a certain point there's wave interference, and now it's the next thing I'm going to tell you, because this wave interference will be important for detecting these particles. So the idea is that while a single field flux, a single wave looks really like a cosine at a certain point in space, more stop looking like a cosine, and they get some decoherence. So, and the easiest way I can see that is by taking two of these things and summing together. So instead of doing this integral that I don't know how to do, what I do, I take I approximate phi like ak1 e to the I omega k1t minus I kx k1x. Okay, this will be for one of these. Then I take another one, ak2 e to the I omega k2t minus I kx. Okay, I take just two of them. Of course, I can take all of them. So I have two now. Okay, in principle, I have infinite of them. This A1 and K2, they are basically statistically at around the peak of the distribution. Okay, it's not like the one of the two is okay. This AK1 and AK2 are of the same order. They're not like one 10 to 10 larger than the other. So what I do now is I evaluate this phi at x equal to 0 in my detector. My detector is at x equal to 0. And then, okay, the e to the ikx kind of goes away. So, and then I take as a factor ak1. So ak1, like e to the I omega k1t, no? And I have 1 plus ak2 over ak1 e to the I omega k2t minus omega k1t. Okay. Okay. This is my very simple algebra. I just took a1 e to the ik1 as a factor. So this exponent I write as e to the I. So this exponent I write e to the I t t, okay, or maybe 2 pi t over tc. Tc is also known as coherence time, and what is it? Well, it's given by the inverse of the difference between these omegas. These omegas, however, are given by this, no? They're given by mv squared, and when 1 plus v squared. When I take the difference of the omegas, the m cancels. I remain only with the v squared. So this tc is of order 2 pi over m delta v squared, no? Because I am, so delta v is basically v1 minus v2. Okay, in general, okay, I have a whole distribution. And this tells me something interesting. This tells me that so while t is much smaller than tc, I can basically throw away this factor. ak1 and ak2 are the same order, so this is over the 1. This is over the 1. I can throw away this factor because only I have 1. So if t is much less than tc, I have my cosine wave in my detector, in my point x equal to 0. So here I have a proper cosine, proper cosine. Instead, as t starts becoming larger than this coherence times tc, what happens instead is that the second term becomes relevant. No? Becomes because the k1 is over the 1, so this completely changes my cosine. And then what happens is that let me continue here. At the time tc, there's some craziness going on, but okay, maybe I don't have space there. But after that, let me do it a bit more properly. So I have my my cosine at the time tc. There is some weird behavior, but then I still get my cosine. So basically, these oscillations will last. This coherence oscillation will last for a time tc, this coherence time. After that, they will dephase, and then I will get again this oscillation for this coherence time. So this is called coherence time now because it means that at the primary detector, the field looks like a single cosine for the time. And this is an important property because these coherence properties of the dark matter will be translated into the coherence properties of the electric field that you produce in your detector when you want to couple this, when you want to detect this dark matter. In fact, this electric field, the electric field that we produce will be also coherence over this time. So, what is the coherence time? Coherence time in numbers is basically 10 to the 3. Okay, 10 to the 6 larger than 1 over m. Okay, it's like 10 to 10 to the 6. Okay, divided by m. Just very okay. Maybe the 2 pi is not too important for now. So the field. Okay, now maybe I should show some video. So we same argument as this. Now I'm thinking what I should delete. Maybe this one. With the same argument as this, I can actually, it's easy to show that the field itself is homogeneous over some sort of some coherence length. So the field is oscillating, okay, coherently for this coherence time, which is 10 to the 6 over the mass. But the field is also coherence over length space. And the coherence length, if you want, is easy to see that is lambda coherence length, coherence, is over the order of lambda W. So in other words, means that okay, you can do the same argument and see that maybe it's obvious, but the field at a certain time t will change only for lengths that are larger than lambda W. So lambda W, which is basically I didn't delete it. It's around 1 kilometer for m to the minus 6 CV. So the picture is that in the end, the light dark matter field in our universe, in our galaxy, will in fact look like a bunch of blobs. So and this I show a bunch of blobs that are also known as quasi-particles, where basically the typical size is of the order of the W wavelength. And inside the blobs, the field is in fact homogeneous, and it changes only after you go below above the W wavelength. And in fact, inside these blobs, the field is oscillating coherently. It's oscillating like a cosine. And the idea is that the blobs will travel at a velocity of these quasi-particles will travel at velocity 10 to the minus 3 the speed of light, and they pass through the detector. So, and while they pass through the detector, they do 10 to the 6 oscillations. Now, because these blobs go like with velocity 10 to the minus 3. Inside the field is coherent, so the typical time I have at my disposal where the field is homogeneous and okay, and oscillates coherently is of order of the let's say what is the space over the velocity? No, so the space is of the order the W wavelength. No, lambda W dB lambda dB, and the velocity is of order 10 to the minus 3. So lambda W is 1 over okay, is 1 over m times 10 to the 3. So long story short, so this will be the velocity, so v 10 to the minus 3. Long story short, the idea is that these blobs pass through you with a velocity 10 to the minus 3. They have a size of 10 to the 3 times over 1 over m. And in the end, you get a 10 to the 6 over m for a typical time, which is basically this coherence time. No? So these particles are low and they're big. So while they pass through you, they take 10 to the 3 over m to pass through you. And in the meantime, no, the field has oscillated 10 to the 3 times. So in the end, you get 10 to the 6 coherence oscillations. So you have to think that when you detect this ultra dark matter, you're here with your detector. One of these stuff passes through you, and they will. And you will use the coherence of the field inside it to enhance your signal. I just wanted to show a video because I think it's better to actually show this. Okay, I know how to do it. Maybe. I don't know. I know. Yeah. Let me share. Or maybe. No, so in this video, I will show you, I will just show proper numerical simulations of the ultra dark matter field. So the idea is that, oops, this is how the file. So this will be how the field looks. So these are proper numerical simulation. No? So the field you see has this granularity. This granularity corresponds to this. So this will be the density field, which I will discuss. I will discuss to you now. This granularity corresponds to these quasi-particles, and these things in fact oscillate. No, so this will be a formation of the dark matter halo. This actually will. So yeah, like my halo forms, and these are these quasi-particles now that have this behavior that I just told you. It's just of course, here I also include in the gravitational potential. No, so instead of having only the free field, I also have gravitational potential. But locally, the thing is not too important. Okay, let me unshare this stuff. And the last thing I want to tell you before going to the theory. Oops. I stop sharing. Okay. Okay, now I see myself there. Maybe not good. Okay. So the last thing I want to tell you is about the density of this the density of these particles today. So the idea is that so let me write it maybe here. So I can in fact calculate the density and see and relate this density the density to phi 0. So if I do it here, if maybe there's some space, but I don't want to. Okay. Okay, maybe let me work it. The idea is that the density is the zero component of the Hamiltonian. Okay. Okay, and the average of the density. So, and in practice, this if you compute this zero component from the Lagrange that I just deleted, is just a half phi dot square plus a half the gradient of phi square plus a half m square phi square. Okay, this is the density. Okay, and then I want to do the average of the density over lengths that are larger than this W wavelength, no, and for times that are larger than this coherence time. And so what do I get? Well, from the formulas there, I basically get a half. Then I have phi 0 square And then I have a sine square from the derivative of cosine. Okay, and then I have okay, and then in front I have omega k square. Okay, and then I do the average of this. Then I do another one, phi 0 square. Then I have k square, another sine square, and then I have a half phi 0 square m square cosine square. So the idea is that if I do the average over long times, the sines and cosine become a half, not because the average of this sine and cosine is a half. So this becomes a half over these times, a half. And in the end, this stuff sums up together, and I get, okay, a half. Then this k and m will group together to give me an omega k. And I get basically phi 0 square over 2 over omega k. Times omega k square. Okay. Okay. Then if I want to invert this to get phi 0 in terms of the density, phi 0 would be the value. My value of the field will be the square root, more or less the square root, actually, the square root of twice the value of the density divided by omega k square. No, because omega k square is more or less m square. So if you want, I can relate the value of density to the amplitude of my field altogether. Like amplitude of the field will be to the value of the density. So two observations. So this one, if you actually plug in numbers, the value of the field is of order, let's say, 100 EV for 10 to the minus 6 m over m, EV over m, without any power. Okay. So it's sort of large in some units. And in addition, this field will okay, this field would be proportional to the square root of the density, no? So it's proportional to the square root of the occupation number, because the density is proportional to the number density, no? So proportional to the occupation number. So for large occupation numbers, no, this field is large. And if you want, you can think of the square root of occupation number as all particles summing together, these particles summing together in a sort of random walkway, and in the end, no, you get the square root of occupation number coming from the random walk. Okay, and in terms of Fourier transform, just to say the field, the corresponding field. Okay, now to the tilde modulo square. In terms of Fourier transform, I get something like, if I plug in terms of omega k, which is square root of m square plus k square. The fact that it's non-relativistic implies that it's very well peaked at m, and the fact that it's okay. And then there's a dispersion now coming from this 10 to the minus 6, a 10 to the minus 6 dispersion with respect to m. Okay, times m. So if you want, it's a very coherent field with this. Okay, then I don't want to spend too much time about the detection of this stuff, but maybe I will just introduce something. So usually, because people after me will talk about the detection, but the idea is that you use this coherence, basically this cosine that lasts for 10 to the 6 times to enhance signals in a cavity, basically. I don't want to say too much time about this, but to think about this. But I just want to say that usually what you do, you employ couplings of this field to the standard model. This one I don't think I need. You employ couplings of this field to the standard model of the kind that okay, we see much more detail of the kind phi phi electric field times magnetic field. So in the background of a magnetic field, which you might have in your cavity, this field produces an electric field. So I have this in the background, and I produce an electric field. But you see that you have some coherence properties there of the electric of the field, which means that the electric field itself will be kind of produced in your cavity with the same coherence properties. So what actually happens is that the electric field phi will electric field E will actually have the frequency basically given by the mass of the particles. So and you can think of this like having one scalar field coming along, interacting with a magnetic field and producing an electric field. Okay, some electric field. But the fact that this thing is very non-relativistic implies that the energy of the frequency is basically m over 2 pi, and then you have 1 plus v squared over 2. Okay, but okay, this one is small compared to the one. This just because if the field is non-relativistic. So this okay, this stuff is m. So basically all the energy that is in the mass is converted into the electric field. This is different from WIMPs. It's not like for WIMPs you convert all the energy of the particles into electricity. No, you only transfer a small part or maybe some part of the energy to your detector. Anyway, this is just to say that the field is basically converted to electric field. The electric field has a precise frequency given by m, maybe over 2 pi, which is also the order of one of the Compton wavelength. And what these guys do, not me, is to in fact use the coherence of the corresponding electric field in a resonant cavity. And the way you do, you build a cavity with the correct resonant modes, and to do that you need to have a cavity if you want, of length. Okay, very roughly, given by this Compton wavelength. This Compton wavelength. Yeah, but I'm not going to talk too much because it's not my field. But the idea is that you have to build a cavity where you basically can fit one of these modes. So one is electric field, but and the corresponding, if you want, length of this electric field is given by the Compton wavelength. But we said this Compton wavelength is of the order of 1 meter. It's written there, I'm sure. Is of the order of 1 meter. Okay, that we write here. It's order 1 meter. Okay, it's basically 10 to the 3 is more than this for n 10 to the minus 6. Yeah, no, I'm not going to say. Just want to say, so this is, okay. I'm not going to say much about this, but this is basically something related. Just want to say that indeed, you have to build a cavity now with a length of this order, no, in order to resonate enhance this effect. And of course, this mass is a free parameter. So in principle, you have a range of cavities to build. In fact, these guys will yes. Yes. Sorry for not saying. So this is in fact phi f mu nu f tilde mu nu. But we will see next week. Well, next lectures. This I just wanted to say. Yeah, sorry for not saying. Okay, maybe there's a factor of 1/4. Yeah. Okay, with the factor of -4. Okay, you have to basically build a cavity of this size. So you don't know the mass of this field, so you have to scan over many lengths, and this is what basically prevents us to get a definite answer on definite detection for these particles. So, but as also this coherence will last for 10 to the 6 times. So in the end, you can take advantage of this produced coherent electric field if you have if your cavity has a quality factor of up to 10 to the 6, meaning that you can build this resonance signal up to 10 to the 6 times, after which the resonance is lost. And last thing, one of the things I'm doing right now is to, in fact, predict the value of the mass of this particle, because as you see, the mass of this particle is related to the cosmological evolution, and there is a compelling scenario where this mass is predicted, and if you predict the mass in this, if you predict mass, you can basically tune your cavity with the correct length to obtain the resonance you want. Okay, this is basically all I wanted to say about the general property of wave-like dark matter. In the end, this is a very generic picture because it only relies basically on the fact that the field is non-relativistic and it behaves classically because it has a large operation number. And however, just to say, there are also more exotic, not really exotic, but also different scenarios where instead of having waves, the field may be made of compact objects that are called axial mini clusters. So instead of having a wave, the field can be actually made of a mini cluster of a compound that passes through you. Or maybe the field can be made of a bound halo around the sun, because here we have sort of neglected the self-gravity, but in principle, what you can have, you can have a configuration of the field that is bound on the sun, in which case, now you can have larger density and a different velocity dispersion. Okay, this just wanted to say that there are also other scenarios, but this is the, if you want, vanilla, simple scenario where the field is only made of waves. Okay, so this just wanted to say, and this concludes my first part on wave dark matter. So now we have to find the questions. Yeah. The blob is a regional space where the field is homogeneous and oscillates coherently with the frequency given by m. No, so inside this blob, the density is in fact constant. Okay, and the field oscillates coherently with this m. And it is size of W wavelength. Size is lambda W, the W wavelength.
I would have there's no space blocks. Like it's for the drawing. Blocks are touching each other.
Yeah, okay. There's with some overdensities and underdensities. Okay. Here I didn't show anything because in principle there's an underdensity. So there's a big density and there's an underdensity. It was shown maybe in this video, in the video that I showed. There's an underdensity and there's an overdensity. But these things move. They move. They pass through you. But it's nothing but just visual description of the solution. I mean, there's nothing more. Like the solution there. That's a phi of x. It's a visual description of this. There's nothing more than that. Questions? Okay. So now I introduced this field. We still have 10 minutes, right? Itai? We still have 10 minutes.
We have 2 minutes.
But we started late.
Ah, right.
No?
Sure. Yeah, we still need to give them some breaks. So
Okay. No, okay, just want to introduce the next chapter, chapter 2, which is the motivation, the theoretical motivation for these particles. So now we have introduced, okay, now we sort of introduced one of these ultralight particles, and we would like to understand why they're there, if there is a theoretical motivation. And so the first thing I want to say is that basically you don't really have to have a theoretical motivation, because these particles, as we will see, they're produced automatically in the universe in the Mesoscale mechanism, non-thermally, if they're just introduced in the Lagrangian. However, we have in some theoretical bias of why these particles are there, uh, which basically comes from a standard model itself. So the standard model has some problems that we think are serious. In particular, there are some parameters of which we don't understand the size of, and one of them is the QCD the QCD theta angle. And I just want to say, not maybe into too long. I just want to say that one of the compelling solutions of the fact that this theta angle is very small is a motivation for introducing these particles. So just talk about the QCD, so two QCD axion and Alps. So I don't want to say too much about this stuff because it's a sort of textbook story, but maybe it's worth to remind ourselves why we are doing many of these things. So the standard model contains the QCD part of the standard model. So I'm sure that many of you know already this stuff. But QCD part of the standard model contains a term of this kind. So okay, this will be the Lagrangian q bar I dash q plus q bar left and q right plus Hermitian conjugate, Thompson conjugate. So this will be the Lagrangian standard model that contains only QCD. Okay, then there are of course also other terms. This is what you usually write. G is the gluon field, Q are the quarks. This is the covariant derivative with respect to the to the gauge field, and the Q left and Q right are the left and right components of the quarks. So okay, I don't want to spend too much time, but Q left right basically P left right Q. No, it's P left right 1 minus plus gamma 5. Okay, so this Lagrangian per se is not complete. In fact, we have another term of the kind theta 0 g mu nu, g tilde mu nu. No. Theta 0 per se respects all the gauge symmetries. So G tilde is the dual of the gluon field, which is a half epsilon mu nu dot sigma G dot sigma. So this term respects all the gauge symmetries. However, usually it's not shown in the Lagrangian because it's small. It's experimentally very small. So this theta 0 is in fact experimentally very small. And importantly for us, this term in fact has different properties compared to the others because it violates CP. Because this G tilde, first of all, epsilon is a pseudo tensor, so that's why it violates CP. But this G tilde can be written as E dot B, maybe modulus a minus 4 factor. This E dot B would be the column electric, column magnetic field. Okay, so there is an A. But you know that E is parity even, while B is parity well. E is T even, and B is T odd. So the idea is that the variation of CP is the same as variation of T if the theory is as a Hermitian Hamiltonian. But E is parity even, B is parity odd because is T odd because as you can imagine, B comes from, for instance, from motional charges. So if you have some motional charges and you run back time, you run time in the opposite direction, the magnetic field will run in the opposite direction. So this is why B is T odd. Okay. In any case, this stuff violates T and also violates therefore CP. And And it also it has some sort of more weird properties compared to the others because it's in fact a total derivative. So this G nu, this G tilde, in fact, G tilde, right, like this, is in fact a total derivative, and therefore it doesn't really contribute to the classical equations of motion. And also at the perturbative level, it doesn't contribute because when you calculate the classical equation of motion, you throw away all the total derivatives. Okay, and another thing that I don't want to spend too much on is the fact that this term, the term theta zero, the actual physical term is the physical parameter is not really theta zero, but is theta minus the phase or the argument of the quark mass matrix. Because you can always do chiral rotations, axle rotations of the. I think we are almost done. You can always do axle rotations of the quark fields, and in the end, the only invariant combination is this theta zero minus MQ. Okay, I think we are almost over, but. The idea is that experimentally this theta parameter is very much suppressed. In particular, as maybe I will tell you a bit more detail next week, this theta is less than 10 to the minus 10. This comes from measurements of the electric dipole moment of the neutron. And next time we will try to solve we will try to explain the smallness of this parameter via introduction of particle, which is the QCD axiom. Notice that in principle, dimensionless parameters can be small if once asymmetry is recovered. If you put this parameter to 0, for instance, the famous case of the Yukawa model, you recover the chiral symmetry if you put them to 0. In this case, you put theta to 0, you recover CP, but CP is already broken in the standard model by the CKM phase, and this therefore is a problem called strong CP problem, strong CP. Okay, and one elegant solution that also, would make up the dark matter of a universe is the introduction of a new field that is called the QCD axiom. And this new field will have all the properties that I told you in the previous part of the lecture. So next time we will spend maybe half an hour, maybe 20 minutes to talk about the QCD axiom properties, and then we will discuss how this particle is produced in the universe with the Moselian mechanism. Okay, thank you. Questions? Yeah.
So this E dot E from the previous.
Yeah. Yes. So exactly. Maybe we see this next time. But once you introduce the QCD axiom will couple to the gluon with an effective A over FA. A will be the axiom, FA is decay constant in this way. But this coupling also generates a coupling of the kind A over FA, FF tilde at low energy, where F is the photon. This is almost automatic unless you have some crazy model where some UV-IR contributions cancel. And as a result, if you introduce this particle, it's almost guaranteed that the coupling that I told you before appears. That's what makes us happy about the detection of this particle. Other questions?